Welcome back to the deep dive. For years now, we've been tracking the incredible, just the dizzying acceleration of artificial
It's
intelligence.
been a wild ride.
It really has. And for most of that time, the conversation has centered on language. We talked about how large language models, the LLMs, taught machines to speak, to summarize, and to reason with this almost human level fluency.
And that really felt like the big one. That felt like a fundamental, massive upgrade to how we do knowledge work.
It did.
It absolutely defined what you might call the age of language. It was this huge philosophical shift where AI learned to command the symbol set of human thought, which is, text.
But at the sources we gathered for this deep dive, they describe something fundamentally different happening right now. We're witnessing AI learning not just to process words, but to build.
That's the leap.
We're moving from the passive representation of reality, describing a world, to the active structural construction of one.
And that's the core thesis of all our material. Our deep dive today is focused entirely on 3D AI, the rise of spatial intelligence, and the rewriting of digital reality.
Right.
And look, this isn't just about making better video game graphics or generating prettier VR demos. This is what our sources are calling a civilizational shift.
A civilizational shift, that's a powerful claim.
It is, because it's the transition from flat intelligence, which deals only in, surfaces, pixels, and text, to spatial intelligence, which deals in volume, physics, and geometry.
And that's based on a very clear distinction, isn't it?
It is. The core difference is profound. LLMs provided a lens through which to describe reality. They were commentators, they were narrators.
They could tell you about the chair.
It could tell you everything about the chair. But 3D AI, or spatial intelligence, it actually constructs the chair. It shapes it, it simulates it, and it renders it in 3 dimensions. It converts human imagination into geometry, natural language prompts into landscapes, and, abstract ideas into fully navigable, physics-aware worlds.
Okay, so let's really unpack this enormous idea. We're moving from words on screens to worlds in space. If we accept that 3D AI is fundamentally different, what exactly is this dimensional leap? And how does it get past the limits of the incredible 2D image generation, the Midjourneys and DLEs that we already know and use all the time? So where do we start? What is the architect AI?
Well, the best way to start is with a clear functional definition. 3D AI refers specifically to AI systems that generate, manipulate, interpret, and simulate 3-dimensional content using really complex machine learning techniques.
Okay.
Its fundamental objective is simple to state, but, it's revolutionary in execution. Transform human intent into spatial reality.
So it takes the abstract desire, the prompt, and manifests it structurally. It makes sure that structure has integrity.
Precisely. You mentioned the 2D tools, and they operate on uniform pixel grids, which are, flat data structures. Pretty straightforward for a computer. But 3D AI, by necessity, has to work with far more complex volumetric formats. And these aren't just technical terms. They are like the raw materials of digital construction.
Okay, let's pause right there. Before we get into the generation methods, we absolutely must define these complex data formats because they're the foundation upon which this new reality is being built.
That's a necessary deep dive right there. Think of it like this. 3D meshes are the classic high-level surfaces.
So the wireframe you see in old CGI movies.
Exactly. The polygonal framework that defines the exterior shape of an object. It's optimized for rendering, so it's good for shape, but it's actually pretty poor for things like light interaction or understanding the internal density of an object.
Okay, so that's the surface. Then we move to data that actually captures real-world scanning.
That's where point clouds come in. These are just massive collections of individual data points in space, often captured directly by LiDAR sensors.
Like the ones on self-driving cars.
Just like those. They define a scene's geometry with really high fidelity, but they are messy and unstructured. It's just a giant list of spatial coordinates. The AI's job is to interpret that noise into a coherent shape.
So it's like a cloud of digital dust that the AI has to sculpt.
That's a great way to put it. Then you have voxels. You can think of them as the 3D equivalent of pixels. They're tiny little volume elements that break up space into a grid.
So instead of a flat square, it's a tiny cube.
It's a tiny cube. And they are fantastic for modeling internal density like human organs in healthcare from an MRI scan, or liquid dynamics in a simulation places where a surface-only mesh would completely fail.
And finally, the one that our sources say was the real game changer for photorealism. Neural radiance fields. NERFs.
NERFs, yeah.
Why are these so different from that traditional mesh and texture approach?
Because NERFs are a radical departure. Instead of storing the geometry explicitly, like in a mesh, a NERF models the light distribution within a volume of space using a neural network.
Okay, that's a lot to unpack.
It is. Essentially, the network learns what color and density of light you should see from any given point in space, looking in any given direction.
Wow.
This ability to model volumetric light allows the AI to capture really subtle phenomena reflections, translucency, atmospheric effects like fog, things that traditional flat texture maps just cannot reproduce convincingly.
And the power of these formats, especially NeurFs, is that they are structurally real, right? Even in a simulation, you can move through that data.
Absolutely. Think of the illustrative example our sources hammered home for the listener. You can type a prompt like, a floating crystal palace above a neon ocean at sunset.
Classic prompt.
A classic. And the AI doesn't just generate a flat image. It gives you a fully rotatable, editable 3D world, complete with the correct light fall-off and shadows. You could, in theory, walk through that palace, and in a simulated environment, the structure would logically obey gravity and physics.
That immediately illustrates the philosophical shift. This is the moment AI moves from passive representation to active construction.
From narration to manifestation.
Exactly. From telling you about the palace to giving you the physical, volumetric blueprint for it.
It is the birth of the architect AI. And this capability represents a profound democratization. I mean, world building was previously restricted only to elite architects, specialized VFX engineers, or, huge teams of game designers.
And now the power to summon worlds based on geometry is being placed in the hands of everyday users. That sounds like a massive jump from where we were even 3 years ago.
It is.
So how did we get here? Algorithmic world building sounds like science fiction, but this technology is real and available right now.
We've moved through several key evolutionary stages, and we've basically abandoned the historical, slow method of handcrafted modeling. The first major step was the development of those neural radiance fields, we just discussed.
And we know NERFs were incredible for photorealism, but they had a major bottleneck, didn't they?
They did. They were revolutionary but computationally expensive to the point of being impractical for any kind of real-time application.
Why so slow?
To render a NERF, the system has to send millions of simulated light rays through the neural network just to calculate the color and density for every single pixel you see on the screen.
Every frame.
Every single frame. That process, it's known as ray marching, and it is brutally slow. It can take minutes or even hours to train and render a single scene, which completely disqualified them for things like VR or real-time gaming. That was the primary computational bottleneck.
And that's where the next major technological jump, Gaussian splatting, provided the necessary efficiency. How does that technique solve the NERF bottleneck?
Gaussian splatting is the efficiency leap that was required for real-time use. It's a clever workaround. Instead of calculating these complex volumetric light interactions through a heavy neural network all the time, Gaussian splatting replaces the neural network with millions of tiny, independent 3D ellipsoids, or splats.
Splats, I like it.
Each splat has its own color, its own opacity, and its own shape.
So instead of this intense volumetric calculation, it's just rendering a massive number of tiny, simple 3D shapes very, very quickly.
Precisely. It's an order of magnitude faster. Because the splats are simple geometric primitives, they can be rendered efficiently using traditional GPU rasterization techniques that have been around for decades.
So it's playing to the strengths of the existing hardware.
Exactly. This allows for these immersive scenes with unprecedented speed and realism, often rendered at 30, 60, even 90 frames per second. This speed is absolutely critical for high-stakes applications like autonomous vehicle simulations, complex VR environments, and competitive video games.
Right. It's the difference between looking at a beautiful static model and truly inhabiting a dynamic, playable, and reactive environment.
That's it. And finally, we are seeing the application of the technology that dominated 2D, diffusion-based 3D generation.
Okay, so the same engine behind Midjourney.
The very same. Diffusion models are the method for actual novel creation. Borrowed from 2D image generation, they now generate volumetric geometry. They start with random noise and progressively refine it, layer by layer, transforming that noise into fully coherent 3D forms that the user requested via a text prompt.
So NeurFs and Gaussian splatting are great for capturing and rendering reality.
And diffusion is for creating reality from scratch. Together, they represent the transition from painstaking manual modeling to what our sources call algorithmic world building.
So this isn't just one type of AI. It sounds like a complex fusion of different machine learning systems, all working in concert to create a believable world. Let's break down the underlying mechanics that are making spatial intelligence function.
It absolutely is a hybrid approach, and it's defined by four core enabling technologies. First, you have the foundational piece, diffusion-based geometry synthesis.
So that's the engine that turns the abstract text prompt into the physical shape.
Yes, refining random inputs into structured, volumetric environments. That's step one. That creates the raw geometry.
Okay, so you have the raw shape. How do you make it useful and editable?
That's where the second technology comes in, language-guided procedural creation. This automates the incredibly tedious workflows traditionally required in 3D modeling.
So it's like a smart macro system.
A very smart one. Natural language now breaks down the modeling steps. For instance, instead of spending days manually sculpting a complex structure, you can just tell the AI to make the Crystal Palace's columns Greek Revival, add some ivy, and apply a reflected glass texture.
And the AI just executes those complex parameters.
Exactly. It automates the workflow and integrates directly with professional tools like Blender or Unity. It's automating the instructions and the manual steps for the modeler, which in this case is the AI itself.
Okay, that's already a huge leap in productivity, but it gets deeper.
It gets much deeper into simulating actual intelligence with the third and fourth concepts. Third, we have vision language action systems, VLA systems. This is a major area of research right now.
What does that mean in practice?
This is where the AI perceives the space using its 3D understanding. It interprets human instruction in natural language, and then it takes a physical action within that simulated physics-aware world.
That's a huge leap. An action system in a 3D world, this sounds like the precursor to the intelligent robotics.
It is the single most critical stepping stone, which leads directly to the fourth technology, embodied AI.
Right.
Virtual agents actually inhabit these 3D environments, and they learn not just from static data sets, but through motion, consequence, and direct interaction with the simulated physics.
So they learn that if they push a ball off a cliff, it falls. They learn object permanence and cause and effect, not by reading about it, but by doing it.
By doing it, this shift from symbolic, abstract thought to physical, embodied intelligence is what researchers believe is a major stepping stone toward achieving artificial general intelligence, or AGI.
So the simulated 3D environment becomes the ultimate training ground.
It's the perfect sandbox for real-world robotics. The AI learns to predict the spatial consequences of its actions before it's put into a billion-dollar factory or a self-driving car. So 3D AI isn't just about creating pretty digital twins. It's about training the next generation of intelligent agents that will eventually navigate and operate in our physical world.
It's moving AI from abstract thought to demonstrable physical presence. Here's where it gets really interesting for me, because we are no longer just talking about basic research. The immediate consequence of these breakthroughs is that platforms are emerging right now that are productizing this power for creators and businesses globally.
That rapid commercialization is the key to the democratization of spatial creation. If the tools are too slow or too complex, they just remain academic toys.
Right.
But we're seeing these dedicated platforms addressing very specific user needs within the 3D content creation pipeline. They're monetizing the architect AI.
Okay, let's detail these emerging platforms and their specific uses, because they define the emerging market landscape as we speak.
Certainly. So you have platforms like 3D AI Studio, which is focused purely on speed. Rapid text-to-3D model generation, aiming to create production-ready models in just seconds.
So for quick mock-ups and prototypes.
Exactly. Contrast that with Meshy AI, which specifically targets professional game developers. They focus on production-grade assets models that are immediately cleaned, optimized, and usable in a Unity or Unreal game engine pipeline.
So a game studio can eliminate the time sink of simple asset creation. No more week-long modeling tasks for a single unique barrel or weapon. You summon it instantly, and it's game ready.
Precisely. For design professionals who need more visual workflows, we have Spline AI. They offer a visual 3D design workflow tailored for web creators and marketing teams looking for interactive 3D elements for websites.
And what about bridging that gap between a hand-drawn idea and a digital object?
That's where a tool like CSM AI comes in. It bridges the analog and digital divide by focusing on sketch-to-game-ready assets. You can do a quick 2D drawing on a tablet, and it'll turn it into a usable 3D object in minutes.
Wow. And then there are the platforms aiming for total world creation. That's the holy grail, isn't it?
That's the most ambitious segment, for sure. Seal AI aims for conversational creation, of full game environments. You literally talk to it. You describe the mood, the lighting, the density of the foliage, and it builds an entire navigable world around you.
That just radically collapses the time and skill required for massive environment creation.
It's a total paradigm shift. But of course, the foundational research is still being driven by big tech. They're focusing on the infrastructure and the intelligence within these ecosystems.
Right, they're building the underlying engine.
They're building the whole pipeline. Take Meta's SAM 3D, which stands for Segment Anything Model. Its focus is on reconstructing full 3D geometry and textures from a single 2D image.
That's crucial for efficiently populating vast virtual worlds.
It is. You snap a picture of a coffee cup on your desk, and suddenly you have a clean, usable 3D asset for your VR space. It's about data ingestion at scale.
And Google DeepMind is focused on building intelligence within those worlds.
Yes, their Sima 2 initiative, that scalable, instructable, multi-world agent. It creates AI agents designed to reason, explore, and learn inside dynamic 3D environments. They interact with the physics, and they learn through consequence. This directly feeds into those embodied AI systems we were talking about.
But you put it all together.
You put it all together, and these tools collectively do not just generate static objects, they generate entire reactive ecosystems. The sources emphasize that this democratization of spatial creation was once exclusively the domain of elite, highly specialized experts.
Okay, so we've established what 3D AI is and the ecosystem that's building it. But we've used LLMs as the natural benchmark for the AI revolution so far. We really need to clarify how spatial intelligence fundamentally differs from that narrative intelligence. Are they competing or are they complementary?
There are fundamentally different cognitive approaches that are ultimately going to be convergent, but first we absolutely have to acknowledge the functional differences. LLMs think in sequences of tokens.
In words.
3D AI thinks in spatial coordinates, in geometry.
Let's use that comparison table structure from the sources to make this solid. In the core domain, LLMs live in the world of language and concepts. 3D AI operates in space, geometry, and physics.
And this difference dictates the intelligence type. LLMs are sequential thinkers. They are masters of syntax and information retrieval. 3D AI is inherently spatial and physical. It thinks in dimensions, relationships, and structural integrity.
The output reflects this perfectly. LLMs produce words. 3D AI produces persistent objects and worlds.
The key is in the persistence and the integrity of that data. An LLM's output is text, it's ephemeral, you can easily edit it or discard it. A 3D AI's output is experiential. It's a thing.
And that gets to the concept of embodiment.
Exactly. This is where the major philosophical gulf lies. LLMs are abstract, 3D AI is experiential. It creates something that is persistent, auditable, it's subject to physical law, and it can be inhabited.
That contrast brings us to that powerful analogy from the research. An LLM thinks in sentences and can describe a chair. A 3D AI system thinks in dimensions and can generate a chair that has structural integrity, occupies a specific volume, and obeys gravity.
And this comparison underscores why this is the next era. LLMs created the age of language, democratizing knowledge and text processing.
Right.
3D AI is creating the age of simulation. It's democratizing the construction of reality. The AI is moving from being a commentator and a storyteller to being an architect and a universe builder.
And the implication is that the data generated by 3D AI, the digital twin, the architectural plan, is inherently higher value and less disposable than, say, a conversational text output.
It's a foundational asset versus a transient piece of information.
The most immediate point of comparison for our listeners is going to be the difference between 2D generative tools like Midjourney and these new 3D generative systems. They share so much technological DNA, but the outcomes are, well, worlds apart.
They do. But we need to define the differing creative goals immediately. 2D generative AI asks a fundamental question. What should this look like?
It's about aesthetics.
It's all about aesthetics. The result is a picture, a visual illusion that relies on aesthetic priors from its training data. 3D generative AI asks a completely different question. What should this be in space, depth, and physical presence? That produces an environment built on geometry.
And the crucial distinction, as you said before, is that the 2D output remains locked to a single perspective. It's a static canvas, no matter how photorealistic it looks.
Whereas 3D constructs objects in environments that are defined by geometry, depth, scale, and crucially physics-aware properties, the resulting objects are not just seen, they are built to be explored, manipulated, and navigated from infinite viewing angles.
That shift from a fixed viewpoint to infinite viewpoints is the dimensional leap.
That's the leap.
Okay, so let's look at the shared foundations. 3D AI is clearly standing on the shoulders of the 2D revolution, borrowing key architectural components.
They share core pillars, absolutely. Both rely heavily on the diffusion architecture, that progressive noise-to-signal reconstruction process we talked about.
Right.
Both utilize text-image semantic alignment through foundational models like CLIP to make sure the AI understands the relationship between human language and visual output.
So the AI knows what a castle is supposed to look like.
And both use iterative optimization to get to that realism. But importantly, 3D AI relies heavily on transfer learning, adapting the learned aesthetics from massive 2D datasets and trying to extrude them into spatial form.
So it learns what a castle looks like from billions of images and then attempts to build that aesthetic into a geometric volume. But that transition to the third dimension must introduce significant non-trivial complexity.
That is the hard problem. Look at the data structure difference. 2D uses those uniform pixel grids we mentioned, straightforward matrices for a computer to process.
Easy peasy.
Relatively. But 3D has to process irregular volumetric geometry meshes, voxels, point clouds. This unstructured data demands exponentially more complex computation, memory management, and specialized algorithms just to define the boundaries of an object.
And the generation pipeline itself must be inherently more complex for 3D generation. You can't just generate the 3D object in one go, can you?
You cannot. A 2D generation is a pretty direct process. Noise to image. Done. 3D requires a continuous, complex optimization loop.
What does that loop look like?
The AI has to render multiple synthetic 2D views of the 3D geometry it's currently building.
So it's taking pictures of its own work.
It's taking pictures of its own sculpture from every angle. Then it compares those pictures against the original text prompt for visual and semantic alignment, and then it iteratively refines the geometry in 3D space. It's a constant cycle of build, check, refine.
Why is that necessary? Why can't it just build it right the first time?
Because the AI can't be sure the structure is correct unless it views it from all sides. A castle might look great from the front, but without checking the side view, the back could be a hollow, distorted mess. And this multi-step process introduces unique and severe challenges, the chief among them being something called coherence drift.
Coherence drift. I've seen examples of this. That's where the geometry seems to change shape or the texture slides around when you rotate the object. It fails to maintain spatial consistency.
Exactly. The object looks right from the front angle because the 2D prior was strong, but then you rotate it and the side view reveals vague, mushy geometry, or the texture stretches and misaligns in this bizarre, non-physical way.
Like the infamous two-faced Janus cat problem in early models.
The Janus problem is the perfect example of coherence drift. It highlights the fundamental difficulty of synthesizing a whole, consistent volume, rather than just projecting a single flat image. It's about ensuring geometric integrity across the entire 360-degree object.
And all this complexity directly translates into massive computational demand. We're used to generating a high-quality 2D image in, 15 seconds on a consumer GPU. What are we looking at for high-fidelity 3D generation?
The contrast is dramatic. 3D generation for high-fidelity scenes currently requires minutes to hours, and often highly specialized hardware clusters with tons of VRAM.
So it's not something you're doing casually on your laptop yet?
Not for high-end results, no.
Yeah.
This is due to the demanding requirements of ray marching, volumetric integration, and the high VRAM usage needed to process that irregular volumetric data. It's a resource hog, which is why scalability has been such a persistent challenge.
Besides the sheer cost, what are the 4 unique hurdles engineers are currently trying to solve for 3D? We talked about scarcity and consistency.
The sources highlight 4 critical, unique hurdles. First, the one we just discussed, spatial inconsistency or coherence drift. Second, fidelity gaps. This results in that vague, mushy geometry because the 3D models sometimes rely too heavily on low-resolution 2D priors. The objects look aesthetically right, but they feel structurally weak or undefined.
Like a dream object that falls apart when you look too closely. And what about the input problem?
That's number 3. Control complexity. Precision manipulation is much harder in a volumetric space than simply editing flat pixels. Getting the AI to generate a staircase with exactly 14 steps, for instance, requires much more granular guidance than telling a 2D AI to simply include a staircase in the image.
Right. And finally, the big one, data scarcity.
Yeah. High-quality, labeled 3D training datasets are incredibly rare and expensive compared to the vast sea of 2D image data on the internet. Generating quality 3D data requires specialized LiDAR scanners, dedicated photogrammetry studios, and immense amounts of manual cleanup. You can't just scrape it from the web.
But the sources also show that innovation is rapidly closing this gap, with new techniques specifically targeting these technical flaws.
They are. I mean, the pace is incredible. Key innovations are focusing on improving speed and quality simultaneously. We see things like Dream Gaussian, which uses Gaussian splatting combined with explicit mesh reconstruction to improve geometry sharpness and reduce those fidelity gaps.
And what about that coherence drift problem?
A model called Exact Dreamer is improving the generation pipeline by introducing error-aware reconstruction. It knows when the geometry isn't aligned with the prompt, and it knows where to focus the refinement. This is a smarter optimization loop.
And how are they solving the control complexity problem? How do you give the user more direct input?
That's where something called Control 3D comes in. It enhances the user input by allowing sketch and depth-based guidance. You can give the AI a simple 2D sketch or a depth map, giving the creator much more precise control over the final volumetric structure than a text prompt alone ever could.
And the production results of these hybrid inputs are tangible. This is moving out of the lab and into the studio.
Absolutely. The sources note that these hybrid inputs, combining text, image, and video guidance, now achieve 95% shape preservation accuracy and result in 40% faster design iteration cycles. These are massive improvements that make the technology viable for production environments like video games, film, and architecture right now.
So what does this dimensional leap mean for human creativity and the professional landscape? It sounds disruptive.
We saw the 2D AI democratized visual creativity, concept art, illustration, things like that. 3D AI goes significantly further. It democratizes spatial authorship.
It shifts creative power from specialized, highly trained designers to
To the citizen world builders.
2D helps us imagine, 3D helps us inhabit that imagination.
That's the perfect summary. It allows us to construct interactive, rule-bound realities without needing a degree in computer graphics. If the training data is democratized, the construction becomes democratized, which is foundational for the next era of digital existence.
I do wonder, though, if that high-quality training data is still rare and expensive, as you noted, won't this initial democratization only be available to the biggest platforms that can afford the computational costs? It seems like a democratization of access, but maybe not of the source data itself.
That's a crucial, critical point, and it's a real concern. The tools are becoming democratized, but the foundation, the high-quality 3D data, is still highly centralized. This creates a data asymmetry risk.
So the big players control the primordial soup from which these worlds are made.
For now, yes. The platforms are working hard to build tools that allow users to generate data themselves, with phone-based scanning and things like that. But the gap is real. However, the future will be about unifying 2D and 3D. The sources predict an inevitable convergence.
What does that look like?
The future pipeline will be seamless. 2D designs will instantly become 3D models, and 3D environments can be instantly flattened into storyboards or cinematic shots. This seamless transition is foundational for metaverse design, digital twins, and intelligent robotics. The canvas is no longer flat. The canvas has become a cosmos.
Okay, let's transition from creative worlds to a high-stakes, real-world application that demands perfect spatial integrity: autonomous driving. 3D AI is described by our sources as the cognitive backbone of this entire field.
This is the most immediate, critical application of spatial intelligence where failure is simply not an option. Traditional driver assistance systems relied on 2D vision and simple, scripted, rule-based logic. You see a red octagon, stop.
Right, very brittle.
Very brittle. But achieving level 5 autonomy, fully independent operation in complex, unpredictable environments requires the vehicle to construct a living, evolving 3D model of the world in real time.
So the car isn't just seeing the road, it's understanding the road, with depth, distance, motion, predicted intent, and risk all in real time. It's building a mindscape of the environment.
Exactly. The system doesn't just register pixels, it understands geometry. It is the intelligence that transforms chaotic sensor input into cohesive spatial awareness, translates prediction into planning, and awareness into precise movement.
To build this living 3D model, the vehicle needs to be saturated in data. What are the key sensors fusing information to create this spatial intelligence?
It's a complex multimodal integration process running constantly. The vehicles use high-resolution cameras for visual recognition and context.
That's the 2D part.
That's the 2D part, but then they use LiDAR, light detection, and ranging for creating those dense point clouds we talked about. That's the backbone of geometric distance measurement.
And radar.
They use radar sensors for measuring speed and distance through adverse weather conditions where cameras and even LiDAR can struggle. And finally, ultrasonic sensors for low-speed maneuvering and inertial measurement units, or IMUs, for understanding the vehicle's own motion. All that chaotic, multimodal data flows into the 3D AI processing stack.
And within that stack, what 3D formats are being processed and modeled? We've heard these terms, but how do they function specifically in a vehicle moving at highway speed?
They're processed primarily through those point clouds from the LiDAR, which define the external geometry. But the AI also uses techniques like NERFs and Gaussian splatting for reconstructing fine details like road markings and predicting light behavior in low visibility. Critically, it uses signed distance fields, SDFs, and voxel grids for what's called occupancy modeling.
Okay, SDFs sound crucial for the vision-only systems, like Tesla's. How do they infer geometry without having a LiDAR?
SDFs are brilliant for this. They mathematically represent the distance from any point in space to the surface of an object. The AI system learns to predict these distances based on the camera vision alone.
So it's inferring depth from shadows, motion parallax, object size.
All of it. By calculating the distance to the nearest surface, a curb, another car's side, it can infer the 3D shape and size of every object without needing a direct depth measurement from a LiDAR beam. And voxel grids help the car discretize space into 3D cells to determine precisely what space is occupied and what space is free to drive through.
And the result of fusing all this information must be instantaneous.
Real-time spatial maps with millimeter-level precision. This forms the digital mindscape the autonomous vehicle uses to interpret chaos as order, 30, 60 times a second or more.
Let's look at the three core functions of 3D AI in AVs, starting with perception. This has to be the most critical.
1. Perception and object understanding is absolutely foundational. A traditional non-spatial 2D system can only see a picture of an object. A 3D AI determines the exact spatial location, speed, direction, future trajectory, and collision probability of everything around it. It's geometric identification and prediction.
The sources provide that fantastic specific example to illustrate the difference between seeing pixels versus understanding geometry.
Yes, the system moves beyond mere identification into predictive spatial relationships. The difference is seeing a pedestrian versus a 3D AI system understanding. A pedestrian is crossing 2.4 meters ahead at 1.6 meters per second and is likely to intersect our trajectory in 1.8 seconds. Apply 10% brake pressure immediately to maintain a safe distance.
That level of detail is just incredible. And this precision is no longer theoretical research. It's commercially deployable.
Cutting-edge models are achieving sub-10 centimeter spatial precision for detecting critical micro-obstacles like debris in the road, lane markings, and curbs. And the multimodal fusion combining cameras and radar, or LiDAR, also significantly reduces perception failure rates in challenging conditions like heavy fog, torrential rain, or deep shadow.
Okay, so that's seeing the world. The second core function is 3D mapping and navigation, which relies on something called SLAM.
SLAM stands for simultaneous localization and mapping. It's the key to creating and using the maps, and it's a continuous dual process. The vehicle is constantly building and updating dynamic maps of the world.
That's the mapping part.
Right. And while it's doing that, it's simultaneously pinpointing its own precise position within that map. That's the localization part.
So it's building its map while figuring out where it is on the map all at the same time. Why is that simultaneous nature so crucial?
Because the world is dynamic and GPS fails. SLAM allows vehicles to localize and predict safe paths, even in GPS-denied environments, like tunnels, underground parking garages, or complex urban canyons where satellite signals bounce off buildings and become unreliable.
So the car becomes a conscious, adaptive agent navigating evolving terrain, not a robot just following a pre-drawn line.
That's a perfect way to describe it. And finally, you move from spatial awareness to action, decision-making, and predictive intelligence.
This is where the AI anticipates the environment using its 3D model.
Exactly. By analyzing that spatial data, not just what's happening now, but what will happen in the next few seconds, the system predicts pedestrian intent, driver behavior in nearby vehicles, merge risks, and accident probability.
It's a shift from reactive driving to
anticipatory intelligence. The AI is always looking ahead, not just reacting to the present. In an emergency, 3D AI executes microsecond-level decisions like a controlled deceleration or an emergency lane switch, decisions that are simply impossible for human reflexes to process and execute quickly enough.
One of the most critical yet sort of unseen functions of 3D AI is in the simulation environment where these autonomous systems are trained and tested.
The role of generative 3D models here is immense. It moves the training from the physical world, which is slow, expensive, and dangerous, to the simulated world.
So they build a digital twin of a city.
They build thousands of them.
Yeah.
Developers use 3D AI to create vast synthetic worlds, which are fully physics-aware and photorealistic.
What's the advantage over training only in the real world? It seems like you'd want real data.
Safety and scale. The real world doesn't provide you with enough dangerous situations to learn from safely. This allows them to simulate literally billions of driving scenarios, including the rare, dangerous edge cases.
Like what?
Extreme weather, complex pedestrian behavior like a child running out between two cars, or impossible road configurations. Things that might only occur once in a decade of real driving. Without 3D AI simulation, they couldn't possibly train for these scenarios safely.
It compresses decades of learning into weeks of model iteration.
That's the practical outcome. This simulation capability compresses decades of driving experience into weeks of model training, creating vastly safer, more robust systems much faster than relying purely on physical mileage. It's accelerating the timeline toward true autonomy.
Now, the major players in autonomous driving are all utilizing 3D AI, but they have these distinct, highly debated approaches. Let's look at the different mindsets, starting with the most controversial one, Tesla.
Tesla famously pursues a highly capitalized vision-only approach. They reject LiDAR, relying solely on camera inputs and transformer-based AI for occupancy modeling.
They use those sign distance fields we discussed to predict the 3D spatial structure of the environment entirely from 2D images.
Right. Their system, FSD, is a pure bet on the power of deep learning to infer geometry without direct depth sensors.
That sounds like a riskier but potentially more scalable approach, if you can make it work.
It is high risk, high reward. It's cheaper to deploy globally because cameras are ubiquitous. But it places immense computational pressure on the AI to solve depth and occlusion problems that LiDAR just solves passively by its very nature.
And in the other corner, you have Waymo from Alphabet, which is the standard for the multi-sensor fusion mindset.
Correct. They exemplify the multi-sensor fusion approach. They combine highly detailed LiDAR, high-resolution cameras, and radar. Their strength is redundancy and extremely high precision, which supports the rigorous operational efficiency required for their robotaxi fleets.
They also rely on highly detailed, pre-mapped 3D urban maps, right?
They do, which is another point of contrast. Tesla aims for a system that can drive anywhere, mapped or not, whereas Waymo operates within specific, heavily mapped domains.
And the hardware backbone for the entire industry often comes from one place.
From NVIDIA, they provide the computational and simulation infrastructure. Their Drive AGX platforms handle the real-time AI processing in the vehicle, and their Cosmos simulation engine is the core for synthetic environment training for major OEM partners like Volvo, Mercedes, and BMW. They are the essential infrastructure provider, the picks and shovels of the gold rush.
What about other key players focusing on specific niches?
Well, Cruise, from GM, focuses heavily on dense city autonomy. They have to be experts at predicting chaotic human behavior in very constrained urban environments. Aurora specializes in autonomous trucking and logistics, which requires precision 3D mapping for highway autonomy. Their challenge is long-distance, high-speed perception.
So the competition here is essentially a competition in building the most robust, accurate, and predictive 3D model of the real world, the ultimate digital twin of the streetscape.
That's what it is. And that competition highlights the enduring challenges. Technically, we still face edge case data scarcity, particularly for rare accidents or complex failure scenarios that break the AI's 3D model.
You can't simulate what you can't imagine.
Precisely. Computational costs remain high, and regulatory uncertainty complicates widespread deployment. And of course, in high-stakes environments like mobility, we must discuss the question of algorithmic responsibility.
The ethical dilemma.
The sources certainly highlight the moral dilemma of algorithmic responsibility in unavoidable accidents. When an AI makes a decision that results in harm, who is legally responsible? The programmer, the owner, the manufacturer. This is a question the regulatory bodies globally are wrestling with right now.
But the societal promise of 3D AI in mobility is transformative enough that it seems we're determined to overcome these hurdles.
The sources are overwhelmingly positive on the long-term outlook. A reduction of accidents by over 70%, the elimination of traffic congestion inefficiencies, the transformation of logistics, and significant reduced carbon emissions through optimized routing. It transforms mobility into something intelligent, adaptive, and predictive.
It seems 3D AI is not a feature for autonomous driving. It is the consciousness of the autonomous machine.
It is the mind guiding the vehicle, transforming sensor inputs into spatial reality. We are building intelligent navigators of the physical world.
Okay, we've seen 3D AI creating worlds for machines to navigate. Now let's explore how it is shaping the spaces we inhabit, digitally augmented reality, virtual reality, and the entire extended reality, or XR, spectrum. Our sources indicate that XR in 2025 is no longer just a passive medium.
That is the core shift. XR has matured from experimental demos into an adaptive ecosystem for design, enterprise training, and social presence. 3D AI is the central intelligence layer that's powering this new generation.
So XR is now an intelligent dialogue between human perception and machine-generated reality.
That's right. And contrary to some of the skeptical narratives that came out of the early metaverse hype cycle, the market data shows that XR is undergoing a quiet expansion, particularly in enterprise and niche consumer sectors.
It's not declining.
Not at all.
Yeah.
We're seeing 18% year-over-year XR growth, with projections of 100 million XR glasses users within the next 5 years. Crucially, the spatial computing market is projected to scale exponentially, reaching over $85 billion by 2030, driven by hardware innovations and, of course, 3D AI content creation.
So how exactly does 3D AI elevate the XR experience beyond just simple visualization?
It provides 3 strategic functions that make the environments intelligent. The first is intelligent content creation.
So less manual work.
Way less. Instead of painstakingly designing every element, the AI can generate entire virtual environments from a simple text command, which significantly reduces asset library costs and development time.
This allows for things like instant virtual tourism or massive game environment creation, but it also enables highly specialized uses.
Exactly. Personalized, high-fidelity environments are built on demand. This is crucial for creating digital twins of physical locations used in urban planning, and particularly in medicine and rehabilitation.
Can you give an example of that?
Sure, an AI-powered XR system can tailor a physical therapy simulation in real time. It can adjust the difficulty and sensory inputs like adjusting the height of a virtual obstacle for someone recovering from a stroke based on real-time patient biometric responses. The environment adapts to the person.
That's incredible. Okay, the second role is the transition to context-aware spatial interaction. This turns the environment into a kind of co-pilot.
This is the core intelligence layer. The AI understands objects in the scene structurally and contextually, regardless of their orientation or the lighting.
And when you integrate that with an LLM,
Then the system becomes a real-time cognitive assistant. A user wearing AR glasses in a factory can point at a machine component and just ask, what does this part do? The AI recognizes the geometry of the part, it accesses an LLM for information, and it overlays a layered visual explanation directly onto the component in the user's field of view.
that dramatically increases the utility in fields like engineering maintenance and remote field service. What is the third strategic role?
Performance optimization. This is a big one. Historically, XR has suffered from latency, lag, and overheating due to the high processing demands. 3D AI is tackling this by optimizing the rendering pipeline.
Okay, let's discuss foveated rendering. How does 3D AI enable that efficiently?
Foveated rendering is a necessary technical trick to make high-res displays work. It uses eye-tracking sensors inside the headset to know precisely where the user's gaze is centered.
So it knows what you're looking at.
Exactly. The 3D AI system then renders that central area at ultra-high detail while sharply reducing the detail level in your peripheral vision.
And you don't notice the drop in quality in the periphery.
Because the human eye can't perceive that peripheral blur easily, this can save up to 80% of the processing power without sacrificing any of the perceived fidelity. Other methods include split rendering between the local device and the cloud, and AI-based frame prediction, allowing lightweight wearables to stream ultra-high fidelity experiences with near-zero latency.
So who are the central strategic powerhouses driving this spatial computing market in 2025? It feels like a few big players with very different philosophies.
There are several distinct approaches. Meta remains the dominant consumer VR giant with their Quest series, holding over 50% of the market share in consumer VR. They are focused on large-scale, social spatial AI and the WebXR ecosystem. They want to own the social layer.
And Apple has positioned the Vision Pro 2 quite differently, focusing less on social and more on high-end utility.
Apple, especially with the powerful M5 chip integration, is focusing on spatial computing as a productivity platform. They're aiming to replace traditional screens entirely and integrating deeply into their highly performant Apple ecosystem. They're bidding on performance and high-fidelity integration with existing workflows.
It's the computer on your face idea.
That's it. And Google continues its work on AI integration into the visual external world. Google is focusing on AI-native AR platforms like Project Astra and their Gemini AI integration. They specialize in AI-powered visual overlays on lightweight AR glasses. They're leveraging their deep ecosystem and their dominance in visual search.
And then you have Microsoft focusing on the high-cost, high-return enterprise side.
Microsoft remains the leader in enterprise mixed reality via the HoloLens. They're focused on high-stakes fields like healthcare, defense, and engineering, where the immediate ROI justifies the high cost of the device. Meanwhile, you have companies like Xreal who have rapidly captured significant market share with lightweight tethered AR glasses, proving the demand for highly portable screen replacement XR devices is high.
So the market is really defining itself by use case. Performance for Apple, social for Meta, and utility enterprise for Microsoft and others.
But one of the longest-standing barriers to mass XR adoption has been motion sickness, or cyber sickness, that feeling of dizziness and nausea.
It results from that sensory mismatch, right? Your eyes see movement in the virtual world, but your body and your inner ear don't feel the acceleration. The lack of sensory concordance throws off the nervous system.
That mismatch is the problem.
Yeah.
However, the breakthroughs we've discussed, the speed, the optimization, the increased frame rates, have managed to mitigate this substantially. The solutions implemented as of 2025 are complex technical breakthroughs designed to reduce that sensory conflict.
Such as the 120, 144 hertz refresh rates and the improved pancake lenses.
Correct. But the most sophisticated solution is physiological sensor-driven scene stabilization.
Okay, what does that mean?
This means the system integrates biometric data from the user heart rate variability, subtle head movements, and it uses that data to stabilize and predict the virtual environment relative to the user's internal physical state, minimizing that sensory conflict.
Wow.
And of course, AR and mixed reality also naturally minimize nausea because they maintain a real-world grounding, which makes them more accessible for extended use.
So looking ahead, what are the predicted advancements shaping the next phase of XR, building on this foundation of spatial intelligence?
The sources outline a future defined by hyper-personalization and ubiquity. We expect to see hyper-personalized reality layers where the environment is dynamically tailored to an individual's preferences, needs, or even their mood in real time.
And we'll see city-scale AR environments for navigation, public information overlays, and urban design simulation.
And the blurring of the physical and digital will accelerate.
Absolutely. The emergence of fully embodied digital twins, not just of objects, but of people and emotion-aware XR environments, will blur the line between digital presence and physical reality. The AI could monitor your emotional state and adjust the environment, the colors, the density, the ambient sound, to optimize your experience.
Ultimately, 3D AI is redefining the architecture of experiential truth.
It is. The canvas has become a cosmos. The question shifts from will XR shape our reality to how deeply we will integrate with this programmable layer of reality and what happens when that layer becomes personalized to you. Okay, let's move to perhaps the most impactful high-stakes application, healthcare. This technology isn't just about entertainment or convenience. It's about bringing life-saving precision to medical professionals globally.
This is where spatial intelligence truly matters. The convergence of 3D AI and XR is transforming medicine from a reactive image reading system into a spatially intelligent anticipatory ecosystem. 3D AI translates flat CT, MRI, and ultrasound data into visual interactive intelligence. Doctors are moving from being image readers to spatial analysts who can inhabit the data.
They are entering the anatomy rather than just viewing a slice of it on a monitor.
That's the core shift. The patient's data becomes an interactive, immersive, volumetric understanding of their own body.
Let's start with the most revolutionary application, surgical planning and real-time guidance.
This represents a massive leap in precision. 3D AI reconstructs a patient's specific anatomy into a high-fidelity holographic model based on their standard imaging data.
Yeah.
Then, using an AR headset like a HoloLens, these complex models are perfectly superimposed onto the patient during the actual procedure.
So the surgeon can essentially see the internal structures, the blood flow, the nerves, the tumors projected directly onto the external body, ensuring perfect alignment.
Precisely. The model can be rotated, zoomed, and segmented mid-procedure, providing unprecedented visual clarity for delicate tasks like neurosurgery or spinal realignments.
And this is where the hard data from our sources really validates the shift.
It does. AI-assisted XR surgical guidance results in up to 87% improvement in accuracy compared to traditional methods and an astonishing 86% reduction in procedural time.
That reduction in time and improvement in accuracy is a direct measure of lives saved and recovery expedited. It's not an abstract number.
Absolutely. Yeah. Furthermore, this data is being shared securely. Decentralized XR systems, which use blockchain-inspired frameworks, ensure that this highly sensitive data can be securely shared across geographies for remote consultation while maintaining strict compliance with regulations like high pay and GDPR.
Okay, the second area is medical training and immersive education. The shift away from reliance on static cadavers.
We're moving into the era of experiential intelligence for training. Instead of working with limited physical models, medical students train within AI-powered XR simulations that feature highly detailed digital organs and responsive virtual patients.
And the system can track their performance.
It tracks hand precision, instrument use, and decision-making for real-time skill assessment, which dramatically accelerates expertise and shortens that long learning curve.
And the third major application is in diagnostics and patient management.
3D AI enhances diagnostic precision by converting those static 2D images into interactive holographic models for bedside evaluation. AI-assisted tools like Query.ai and Carpal.ai are standardizing interpretation accuracy across hospitals, moving clinicians from reading static images to analyzing dynamic spatial narratives, which lets them catch subtle anomalies that human fatigue might cause them to miss.
And finally, how is this impacting therapy and mental health?
In rehabilitation and mental health therapy, XR platforms offer adaptive, measurable treatment. VR is used extensively for stroke rehabilitation, where the AI can customize exercises based on motor recovery.
And for mental health.
Critically, AI-controlled exposure scenarios are used for PTSD and phobias. The AI can adjust the intensity and complexity of the virtual environment based on biometric feedback from the patient, leading to dramatically improved outcomes in areas like anxiety disorder recovery and mobility.
Telemedicine, which was obviously accelerated by global events, is now maturing from simple video calls into an intelligent, immersive ecosystem. Our sources describe AI as the cognitive nervous system of this transformation, connecting experts globally.
Telemedicine XR is transforming clinic-bound dependency into proactive, home-based treatment, bringing specialist care to remote areas. The AI processes multimodal data voice, biomarkers, imaging, and turns it into spatial intelligence that can be shared instantly.
Let's discuss intelligent diagnostics in this remote setting. How does that work?
AI-integrated XR platforms convert a patient's scans into 3D models for collaborative manipulation across continents. A team of doctors in 3 different countries can look at and manipulate the same holographic heart at the same time.
That enables rapid data-backed decisions by multidisciplinary teams.
It does. And these systems are noted for detecting anomalies like tumors and cardiac issues with up to 90% accuracy, and they can automate critical case prioritization via predictive triage.
And remote doctors can now conduct virtual physical exams. That seems impossible without physical touch.
It relies on high-fidelity sensor integration. Physicians can conduct simulated exams using AI-enhanced holographic representations of the patient. This includes real-time depth mapping for wounds and precise biosensor integration for virtual respiratory analysis and heart monitoring.
So the AI is the doctor's hands and ears.
It's monitoring heart rate, oxygen saturation, and movement patterns simultaneously, and it can initiate alerts for deterioration. This simulates physical presence, bridging the distance gap for crucial clinical decision-making.
Beyond the clinical functions, AI is also providing crucial automated efficiency.
The administrative burden in medicine is staggering, and AI is starting to manage a lot of it. Automatically transcribing consultations, generating structured reports, and monitoring medication adherence. This operational relief allows physicians to focus on the emotional connection.
What some call empathy augmentation?
Right. It restores the human core of medicine by reducing burnout and increasing patient face time.
Who are the specialized innovators driving this area of telemedicine XR?
You have companies like XRP Healthcare, which focuses on AI health guidance on the XR ledger, providing vital health tracking and multilingual support for underserved populations. Vesta Teleradiology offers 24/7 AI-driven diagnostics, and Volta Medical specializes in real-time cardiac AI diagnostics, specifically for atrial fibrillation analysis during complex procedures. These players are fundamentally shifting healthcare from centralized institutions to decentralized, networked intelligence.
Despite the staggering benefits, the accuracy improvement, the time savings, the implementation of 3D AI in healthcare faces significant systemic hurdles that must be addressed before we see global deployment.
3 major challenges stand out prominently. First, the complexity of data privacy and security.
Right, IGPA. And GDPR?
Compliance with those is inherently complex when you're dealing with massive, immersive, shared environments containing sensitive medical data that might be streamed across borders. Security protocols have to be exponentially more robust.
Second, the costs are substantial, which creates access issues.
High implementation costs are a major barrier to entry, especially for developing healthcare systems.
Yeah.
You need advanced XR hardware, specialized computational infrastructure, and intense retraining for staff, which requires a substantial upfront investment.
And third, the integrity of the AI models themselves is critical when lives are on the line.
AI bias and dataset integrity pose a critical risk. Since anatomy and medical conditions can vary significantly across ethnic profiles, there is a severe need for anatomically diverse datasets to prevent diagnostic inaccuracies across different patient populations.
So deploying a biased model, however accurate for one demographic, could be fatal for another.
It could. This demands intensive ethical and technical oversight.
The conclusion here is that the future of medicine is volumetric, immersive, and intelligent.
Healing no longer waits for proximity, but the speed of its global deployment depends entirely on solving these infrastructural and ethical challenges.
We've established the massive utility of 3D AI across creation, mobility, and life sciences. Now we have to address the disruptive implications of this shift into what you called the age of simulation.
The disruption is both economic and philosophical. Economically, we are facing dramatic creative workforce disruption. As text 3D creation becomes instantaneous, as you can generate a high-fidelity chair in 3 seconds instead of 3 hours, design professions will have to evolve rapidly or they risk radical downsizing.
The value shifts from manual execution to prompt engineering and quality control.
Exactly. It's a major economic overhaul for industries like VFX, gaming, and industrial design. The era of the citizen world builder changes the financial value proposition of the traditional 3D modeler. The task shifts from creation to curation.
And philosophically,
Philosophically, this technology challenges our very concept of reality and integrity.
you're referring to simulation manipulation risks.
Yes. As AI-generated virtual environments become hyper-real, their influence could easily surpass that of the physical world. This leads to reality dilution. If you spend hours a day in a perfectly tailored, hyper-real virtual environment, the physical world begins to feel less real, less relevant.
So governing the line between the physical and artificial will require an overhaul of our existing identity frameworks.
And potentially new governance frameworks for reality itself, particularly in terms of what constitutes evidence or proof in a court of law.
Let's quickly review the primary technical barriers that still keep this technology from being completely ubiquitous, despite all the breakthroughs.
The major obstacle remains computational intensity. Rendering complex 3D worlds, especially those that must be shared and interacted with by thousands of users, requires immense continuous GPU resources. Cloud services have to scale dramatically to meet this demand.
Which makes instant, high-quality generation difficult on consumer devices without heavy reliance on streaming.
Right. And the ethical oversight required is daunting, particularly in those high-stakes fields. We need clear regulatory clarity and comprehensive ethical guidelines to manage algorithmic responsibility, especially in domains like autonomous vehicles and surgery, where an AI's error can be fatal.
The technical challenge is building models that can not only predict accurately, but also explain their predictions.
Transparency is key.
Despite these hurdles, the pace of innovation points to an accelerated future. What are the immediate future predictions for 3D AI? What are the next frontiers?
We are rapidly approaching fully persistent AI-generated metaverses, worlds that exist even when you log off, continuously evolving based on user input and simulated agents. We will see the emergence of sentient virtual agents that inhabit these worlds and communicate using LLMs.
And a full digital twin of our physical cities.
Exactly. Urban planning and infrastructure management will be transformed by factorial AI cities for simulation and optimization. And most powerfully, we will see the multimodal hybrids combining LLMs for language and 3D spatial engines, unifying description and construction into a single, seamless interaction point.
AI will not only understand the world, it will generate new ones entirely on demand.
The cosmos is being programmed.
We've covered a profound civilizational transformation today. We saw the shift from flat intelligence, which describes, to volumetric geometry, which builds. We saw how this technology is driving level 5 autonomy, reshaping XR experiences through performance optimization, and delivering life-saving precision in medicine, sometimes achieving up to 87% improvement in surgical accuracy and an 86% reduction in procedural time.
If the printing press democratized knowledge and LLMs democratize language, 3D AI democratizes reality itself. This new era of spatial creativity means humans no longer just imagine worlds, they summon them into existence. This is the intelligence that learns not just to speak, but to build structurally sound, physics-aware, inhabitable universes.
The age of spatial intelligence has arrived, transforming every facet of our lives, from the roads we drive on to the operating tables we rely on.
And since 3D AI is poised to generate hyper-personalized, persistent virtual worlds, the ultimate digital twins, consider this final provocative thought for you to take with you. If AI can create a precise digital twin of your city for urban planning, and an interactive digital twin of your body for surgery, what does it mean for you to have a persistent, personalized digital twin of your entire identity, a fully realized spatial projection of self? And how will you govern its existence and its interaction with the hyper-real world it inhabits? That is the ultimate question of the age of spatial intelligence.